If you've been tracking the rapid evolution of AI agents, you've probably noticed a recurring pattern. Every time a new domain breaks through, math, coding, terminal operations, it's because researchers crack the code on scaling training data with reliable, automated feedback. The recipe is called reinforcement learning with verifiable rewards. You give the model a task, it tries to solve it, and a strict, deterministic program tells it exactly how well it did. That feedback loop has driven massive leaps in capability. But when we try to apply it to computer use agents, the kind that actually navigate real software, click buttons, and manage files, we hit a hard structural wall. Here's why. In math or coding, a problem statement and a final answer are enough to train a model. But for a computer use agent, a single training example isn't just a question and answer. It's a three-part package. You need a clear task instruction, a fully configured digital environment, and a reward function that can reliably score the outcome. Handwriting these triplets takes hours of expert effort. And if you try to scale them up, you quickly run into a brutal trade-off. You can either keep the reward signals perfectly accurate, but cover only a handful of applications, or you can scale broadly and rely on visual models to judge the results, which introduces enough noise to destabilize training. That's exactly what the CUA-GYM team set out to solve. They built an automated pipeline that generates all three components at once, using a clever adversarial setup. Imagine a test-making competition between two AI agents. The first agent, the generator, builds the initial software state and the target environment. The second agent, the discriminator, is tasked with writing the grading rubric. But here's the critical design choice. The discriminator is completely locked out of the generator's workspace. It cannot see how the files were built or what the setup code looks like. It only sees the original task description and the final environment states. This creates what the researchers call an information barrier. It forces the grading system to actually measure whether the task was completed correctly, rather than just reverse engineering the setup steps or cheating by reading the answer key. The two agents iterate back and forth until the rubric perfectly distinguishes between a failed attempt and a successful one. But how does the grader actually score a complex, multi-step workflow? It breaks everything down into smaller, verifiable components. If the task is to configure file associations in a code editor, the reward script doesn't just check a single Boolean flag. It checks multiple conditions. Does the setting exist? Does one file type map correctly? Does the other? Each piece carries a specific weight, so the agent earns partial credit for progress while being steadily pushed toward a perfect finish. This granular scoring means the model learns exactly where it went wrong, rather than just getting a binary pass or fail. Early versions of the pipeline tried to award points for superficial actions, but the information barrier automatically caught those attempts and rejected them, forcing the system to build rewards that actually measure correctness. It's a fully automated way to prevent shortcut learning and reward hacking without needing human reviewers for every single task. Scaling tasks alone isn't enough if the agents only ever practice in the same narrow set of applications. So the team took a second, equally important step. They scaled the environments themselves. They built CUA-GYM-HUB, a library of 94 mock web applications and desktop workflows. These aren't static screenshots or fragile real-world websites. They are fully interactive, programmable sandboxes that mimic the actual software stacks used in email clients, project management tools, spreadsheets, and cloud dashboards. Because they're synthetic, you can reset them instantly, inject custom data, and run thousands of parallel training sessions without worrying about login screens, rate limits, or unpredictable server behavior. This turns the environment from a bottleneck into a reusable training substrate. The results of combining these two approaches are striking. When they trained open-source models on over 30,000 of these verified task-reward pairs, the agents didn't just memorize specific workflows. They learned to generalize. On standardized benchmarks, the trained models jumped by over 10 percentage points, outperforming previous open-source competitors at similar scales. Even more importantly, they transferred their skills to completely unseen, real-world browser benchmarks. The researchers also mapped out how performance scales. They found that both data volume and environment diversity act as independent levers. Training on a wider variety of applications directly translates to more robust agents, proving that exposure breadth matters just as much as raw task count. There's also a fascinating side effect that emerged during training, which the team didn't explicitly program. As the models optimized against these verifiable, granular rewards, they spontaneously learned to batch multiple actions together. Instead of clicking a menu, waiting for a UI response, and then typing, the agents naturally started chaining predictable, deterministic steps into single, efficient moves. This emergent behavior compressed their action sequences by nearly half, cutting down both training compute and inference latency. It's a clear signal that reinforcement learning is teaching agents not just to complete tasks, but to work efficiently. By automating the creation of verifiable training data and scaling the digital environments themselves, CUA-GYM removes one of the biggest bottlenecks in agent development. The pipeline keeps costs manageable by using targeted language model calls and efficient virtual machine provisioning, generating each example in a fraction of what manual annotation would cost. And because the team is open sourcing the entire synthesis pipeline, the dataset, and the synthetic environment library, the next wave of computer use agents will likely be built on top of this foundation. Imagine asking an AI to check a Slack message, build a presentation, and export it as a PDF. To a human, that's a standard workflow. To most AI models, it's a maze of disconnected tools that don't naturally talk to each other. CUA-GYM bridges that gap. It's not just about teaching models to click buttons. It's about teaching them to plan, verify, and adapt across entire software ecosystems. And as these agents get better at navigating the messy, interconnected world of modern desktop workflows, we're moving one step closer to AI that doesn't just talk about work, but actually does it.